Hello, this is the section 5.7 lesson. In this section we're going to introduce a hypothesis test called a goodness of fit test. Now this test works a little bit differently than some of the other tests we've talked about, but we're going to use the same terminology and the same basic 5 steps. So first of all, let's give a brief overview of what we're doing in a goodness of fit test. So in a goodness of fit test, we've got some population that's divided into several different categories. And we are making a claim about the distribution of these categories. So for instance, we might claim that a certain percentage of the population fits into the first category, another percentage fits into the second category, so on and so forth. The data that we go out and collect are going to be observed frequencies of the categories. So we're going to go out, we're going to get a sample of our population, we're going to count how many in that sample fit in the first category, how many into the second, and so on and so forth. And kind of informally, what we're testing is if the claimed distribution fits the data that we collect. And that's where the term goodness of fit test comes from. So to illustrate this particular test, let's look at example 572. In 1996, the colors of plain M&M candies were distributed as follows. 30% were brown, 20% were yellow, 20% red, and 10% fall into these other categories. And what we want to test is the claim that the distribution today is the same as it was in 1996. So notice that what we've got here is a population of plain M&M candies today. And this population is divided up into 6 different categories. Each color is a category. And here we're making a claim about the distribution of those categories. We want to determine, does that distribution from 96 fit today's candies or not? Okay. So let's look at some data that we've collected. So one of my previous statistics classes, one day we got a big bag of these M&M candies, and there were 1,191 candies in that bag, and we counted the number of each color. So we got 154 brown, 201 yellow, 146 red, and so on and so forth. So there's our data. Our data are observed frequencies of these different categories. Now, let's start setting up our hypothesis test, and we're going to go through the same basic 5 steps. The first step in any hypothesis test is to define the parameters. And so the parameters that we're going to define here are P1 is the proportion of all candies today that are brown. P2 is the proportion of all candies today that are yellow. P3 the proportion are red. P4 the proportion that are orange, so on and so forth. So I've really got one population here with 6 different parameters. So this is already starting to look a little bit different than some of our other tests, but that's okay. Now the next part of this step is to state our hypotheses. Now our hypotheses here are going to look a little bit different than before. So in this case, our null hypothesis is going to be just a mathematical statement of our claim. Our claim is that the distribution today is the same as it was in 96. So in mathematical terms, the claim is that P1, the proportion of brown candies today, is the same as it was in 96, 0.3. The claim also states that the proportion of yellow candies today is the same as it was in 96. 96 it was 0.2. So P2 equals 2. That's another part of our null hypothesis. P3 is the proportion of candies today that are red. In 96, that proportion was 0.2. And so part of our null hypothesis statement that P3 equals 0.2, and so on and so forth. So we've got really 6 different equations that are all part of our null hypothesis. Now the alternative hypothesis is going to be just the opposite of the null hypothesis. The alternative is the statement that at least one of these proportions is different than claimed. In the alternative hypothesis, we're not going to have a less than sign or a greater than sign or a not equal to sign. So we're not going to have a left, right, or two-tailed test. The alternative hypothesis in a goodness of fit test is always this statement here, that at least one of these proportions is different than claimed. The null hypothesis is always going to look something like this. It's the statement that these different proportions equal some claimed value. Okay. Now the second step is to calculate the test statistic. And so let's talk about how this is done, and we'll talk a little bit about the theory behind it. So to calculate this test statistic, we're going to organize our information in a table. So in the first column, I've got my different categories here, which is my different colors. Second column, I have my observed frequency. So this is the data that I collected. Okay? And remember, the sample size was 1,191. If we add up these 6 numbers, it come out to be 1191. Okay? In the next column, we're going to calculate this quantity E sub I, which is the expected frequency if the null hypothesis were a true statement. Okay? So the part of the null hypothesis says that 30% of our candies are brown. So if we take 30% of our sample size, that comes out to be about 357. So if the null hypothesis were true, I would expect in a sample of size 1191 to see about 357 brown candies. Now likewise, the null hypothesis says that 20% of our candies are yellow. So if I take 20% of 1,181, I get about 238. So if the null hypothesis were true, I would expect to get about 238 yellow candies. And then we do the same for these other categories. And so we have here these columns of the observed frequencies and the expected frequencies. Now let's just compare these two columns real quick and think about what it means here. So if my null hypothesis were true, I would expect to see about 357 brown candies in a sample of this size. But what I actually saw was 154 candies. Those numbers are quite a bit different. If I look at yellows, I would expect to see about 238 candies, but what I actually saw was 201. Now those two numbers are not that much different. If we look at some of these others, like down here, this says we would expect to see about 119 blue candies, but I actually saw 247. So there's quite a bit of difference there. So the fact that there's really quite a bit difference between this column here and this column here is an indication that my null hypothesis is probably not a true statement. So I would probably want to reject that null hypothesis. So in our test statistic, what we need here is kind of a total measurement of the difference between these two columns. So the way we're going to measure this is with this simple formula right here. We're going to take each observed value, subtract the corresponding expected value, square it, and divide by the expected value. And we do that for each category, and that's what we have here. You can verify these calculations on your own. And then in the last step, we are going to add up all these numbers right here. And so here's our test statistic, 448.9. And we're going to call that test statistic C. So that's all there is to calculating the test statistic. Now, let's make some observations here about this test statistic. So here's the calculations that we just did. So this test statistic C, kind of informally, is a total measure of the difference between what was observed and what was expected if the null hypothesis were a true statement. So it's a measure of just how much difference there is between these two columns. So if we have a small value of C, that means that there's not a whole lot of difference between what we observed and what we expected. And so that means that our null hypothesis is probably a true statement. So that would cause us that would lead us to the technical conclusion of do not reject the null hypothesis. However, if we had a large value of C, that would indicate that there's a lot of difference between these two columns, and that would mean that the null hypothesis is probably a false statement, and that would cause us to reject the null hypothesis. So that's kind of the basic idea of what's going on there. A small c indicates that we would not reject the null hypothesis. A large value would cause us to reject the null hypothesis. Well, now the next question is, well, just how small does c need to be? Or likewise, just how large does c need to be to cause us to reject the null hypothesis or to not reject the null hypothesis? Well, the theory behind the answer to that question is Theorem 571, which says that if the null hypothesis is a true statement, or if the null hypothesis were a true statement, then our test statistic is an observed value of a random variable with a chi-squared distribution. Now, the chi-squared distribution is one of those distributions from the end of chapter 3 that we kind of skipped over. So let's briefly talk about the chi-squared distribution. Chi-squared distribution is denoted with this symbol right here. This is the Greek letter lowercase chi, chi-squared. And here's some graphs of some different chi-squared density curves. So first of all, a random variable with a chi-squared distribution has non-negative values. And there are different numbers of degrees of freedom, like what we have with the student t distribution. Here's a density curve for 3 degrees of freedom, and there's 5, and there's 9, and so on and so forth. And so when we talk about a chi-squared distribution, we have to mention the degrees of freedom. And this chi-squared distribution is sometimes denoted with this symbol right here, chi-squared of n. The n is the number of degrees of freedom. Okay. Now, like with other types of distributions, we have critical values. And with chi-squared distribution, we have critical values that are denoted by this, chi-squared sub p of n. And here's kind of a formal definition of a chi-squared value. But kind of informally, what's going on here, chi-squared is a number such that the area underneath the density curve is equal to p. The area to the right is equal to p, and the area to the left is 1 minus p. That's the basic idea behind a critical value. Now, what's significant about these critical values is that this critical value is like a cutoff between a small value of c and a large value of c. A test statistic less than the critical value would be considered small. The test statistic greater than the critical value would be considered large. Now, when we look up critical values for this chi-squared test, the appropriate number of degrees of freedom is equal to the number of categories minus 1. So in this case, I have 6 colors, 6 categories, so I'd have 5 degrees of freedom. Okay. Now, this subscript p here in our definition is going to be our significance level, which is typically 0.05 unless otherwise indicated. Now, these critical values can be found in table C4 from the back of our textbook. So across the top of our table we have P, which again is our significance level. So we're typically going to use this column right here. The left column is our degrees of freedom. Here in this table I denote it R rather than N, but it doesn't really matter what we call it. And so we just choose our appropriate number of degrees of freedom from that left column. Okay, so going back to our example, step 3 of the hypothesis test method is to find our critical value. And so we're going to use the default 0.05 significance level. We have 6 categories, so 6 minus 1 is 5, so we have 5 degrees of freedom. If we use a 0.05 significance level, there's our critical value, 11.07. So that is our cutoff between a small value of the test statistic and a large value of the test statistic. Now, our p-value for a goodness of fit test is always an area underneath the chi-squared density curve to the right of our test statistic. Goodness of fit tests are always right-tailed tests. We don't have right, left, and two-tailed tests. They're always right-tailed. So it's the area to the right of our test statistic. Now in this case, our test statistic is this very, very large number, and the area to the right is approximately 0. Here in a bit we'll see how we can find this p-value on our calculator, but you can just imagine with such a large value of the test statistic, there's not much area to the right, so the p-value is 0. Now, step 4 of our hypothesis testing method is to state the technical conclusion, which is always either reject the null hypothesis or do not. Now, let's talk about a couple of different criteria that we can use to come to our technical conclusion. One criteria is to compare our test statistic C to the critical value. And we reject the null hypothesis if C is bigger than the critical value. and we do not reject the null hypothesis if C is less than the critical value. Again, this critical value is like a cutoff between a large value of C and a small value of C. A small value of C would indicate that there's not a whole lot of difference between the observed and the expected, which means that the null hypothesis is probably a true statement. If C is greater than the critical value, then that means there's a lot of difference between the observed and the expected, which means that the null hypothesis is probably a false statement, so we should reject it. Now, if we want to use p-values, we can use the same criteria that we've always used. We compare the p-value to the significance level. If the p-value is less than the significance level, then we reject the null hypothesis. Otherwise, we do not. So here's two sets of criteria that we can use. At first glance, it looks like this criteria is opposite of this criteria down here, but really they're just different ways of coming to the exact same conclusion. In one of them, we compare the test statistic to critical value. Other one, we compare the p-value to the significance level. Either way should come to the same conclusion. Okay? So in this case, our test statistic was this large number, which is much, much larger than our critical value. And so by this criteria here, we would reject the null hypothesis. If we look at the p-value was very small, much less than 0.05. And so we again would reject the null hypothesis. So that's our technical conclusion, reject the null hypothesis. Our last step is to state our final conclusion in non-technical terms. Now, the way we've typically done the final conclusion in previous sections was to look at, does the original claim contain equality, and so on and so forth. Well, we don't really have that here, but let's make a note here that the null hypothesis is really the same as the claim. Right? The null hypothesis was just a mathematical statement of the claim. So they're one and the same thing. So we rejected the null hypothesis, so that means we would reject the claim. So our final conclusion is that there is sufficient evidence to reject our claim, that the distribution today is the same as it was in '96. So that means, in even less technical terms, it appears that the distribution of colors has changed. It's not the same as it was in '96. Now, exactly what is the distribution today? I don't know. We'll analyze that question a little bit more later, but all we can say right now is that it looks like the distribution has changed. So the test that we've done here is called the chi-squared goodness of fit test. And there are two basic requirements. Number one, the data have randomly been chosen, which is always a requirement. And furthermore, those data represent observed frequencies of each category. So our data have to be counts. They can't be things that we go out and measure. They've got to be just counts. They've got to be whole numbers. And then the second requirement is that each expected frequency is at least 5. And both of those requirements are met here in this example. Now next, let's talk about how we could do this test on the calculator. Now, one caveat we have to give here is that what we're going to talk about here only works on the TI-84 calculators. It doesn't work on the 83 calculators. So if you have an 83 calculator, you have to do this by hand. If you have an 84, you can do it on the calculator. First thing that we have to do is enter our observed and expected frequencies into lists. So go to the Stat, Edit menu, and enter your observed in L1 and your expected in L2. Now we do have to manually calculate the expected values. The calculator will not do that for us. So enter those values. And then next go to the Stat Tests menu, and then scroll up or down to option D for the chi-squared goodness of fit option. Now the TI-83s won't have this option. All the calculators have option C, the chi-squared test. That's not what we're doing here in this section. We're going to talk about the chi-squared test in the next section. This section we're doing the chi-squared goodness of fit test. Now if you hit enter, you'll see a window that maybe looks like this. In the first two rows we need to enter the list containing the observed and the expected values. The default value should be L1 and L2. If not, you can just enter those. And then next we have to enter the appropriate number of degrees of freedom, which in this case is 5. The calculator will not automatically calculate the degrees of freedom. Now we've got two options from the last row, either calculate or draw. If you select calculate and press enter, you should get a window that looks like this. So we see that we did the chi-squared goodness of fit test. Here's our test statistic. Now the calculator calls the test statistic chi-squared rather than c, but that's okay. And then next it gives us the p-value. So p is 9.2 e negative 95. So this has really got 94 zeros in front of the 9. So that p-value is an extremely small number. For all practical purposes, it equals 0. Next, it outputs the number of degrees of freedom as we entered it. And then lastly, it outputs this, CNTRB, which stands for contribution. And if you notice the dot, dot, dot there, that means that there's more to the right. So if you scroll to the right, it's going to give you a whole list of numbers. Now, what are those numbers? Well, if we look back at our manual calculation, this list of numbers here is the same as our last column of calculations. Notice that this number here matches up with that number right there. Now, why would it output those contributions? Well, remember what we concluded is that it appears the distribution of colors has changed. So that might lead us to ask, well, which colors have changed the most? Well, we can get an informal answer to that question by looking at these numbers over here. Basically, the bigger the number, the more things have changed. So if you look at like the yellow, this number is only 5.8. That means that it looks like the distribution of yellow candies hasn't changed a whole lot from 96 to today. However, if we look at like this number here, 137, that means the proportion of blue candies has changed quite a bit. So kind of it looks like maybe today 20% are still yellow, but it's not the case that 10% are blue today. That number has changed quite a bit. Well, next on our calculator, just for fun, let's go back to the chi-squared test. But instead of selecting calculate, we select draw and press enter, and we should get a window that looks like this. And so what this does here, it gives us a graph of our chi-squared density curve with 5 degrees of freedom. Gives us our test statistic there, and then it would shade the area to the right of our test statistic. Now it's hard to see here because our test statistic is so large, it's way over here on the right. And it gives us our p-value there of 0. So this draw menu, just draw option, just gives us a graphical representation of our p-value. Now, one last variation here. We've determined that the distributions of colors has changed. Well, let's test the claim of a different distribution. Specifically, let's test the claim that the colors appear with equal frequency. So there's 6 different colors there. They occur with equal frequency. That means that 1/6 of them should be brown, 1/6 should be yellow, 1/6 should be red, and so on and so forth. So if we go through the steps again, we'll go through the same 5 steps that we did before. The first step is to define the parameters. Well, it's the exact same as what we had before. Now our hypotheses are going to be a little bit different. Here we're claiming that everything is has the same proportion. So the hypothesis is that P1 equals P2 equals P3 equals 1/6. And the alternative is that at least one proportion is different than claimed. Now, step 2, let's calculate the test statistic, and specifically all we really need to calculate here by hand is the expected frequencies. So remember we had a sample size of 1191, and so each expected frequency is going to be that sample size times the claimed proportion of 1/6, which comes out to be 198.5. So each category has the same expected frequency. Now let's go to the calculator to calculate the test statistic and the p-value. So again, we need to enter our observed values and our expected frequencies here in the table. The observed values haven't changed, but these expected frequencies have all changed, so we enter those. Now we go to the chi-squared goodness of fit test. We don't really need to change anything there. Nothing has changed. Hit calculate, and we get this result right here. So here's our test statistic of 35.5. Notice that's a lot smaller than it was before. Here's our p-value. It's 1.1 times 10 to the negative 6. So the p-value is still a really small decimal, not quite as small as it was before. And so if we come to our technical conclusion using the p-value, well, the p-value out to 4 decimal places till 0. So it's still less than 0.05. And so we would reject the null hypothesis. And we would conclude that there is sufficient evidence to reject the claim that the colors occur with equal frequency. So in even less technical terms, it appears that the colors do not occur with equal frequency. However, note that we've got a lot smaller test statistic than we had with the 96 distribution. So that means, kind of informally, that the distribution today is probably closer to an equal frequency distribution than it is to the 96 distribution. So there we go. That's the chi-squared goodness of fit test.